Part C. The volume flow rate at the exit. So now we kind of, covered all our bases here on the inlet. Now let's move to the outlet. What do we need to know about the outlet? Well, first thing, and the most important one, is the continuity equation. And we have, a whole video about the continuity equation and how it works, but let's just do the summary here. If we have nitrogen entering this pipe, okay, and then it's leaving this pipe over here, if there's no nitrogen gathering inside this pipe, that is, as time goes by, you're not going to have more and more nitrogen in there so that the pipe's going to at some point burst open. Nor we have the other way around, that is less and less nitrogen accumulating inside, so that you're going to have a vacuum in there and the pipe's going to burst inwards. Unless one of those two situations happen, then we have what we call the continuity, right, taking place, which means that the mass going in has to be the same as the mass going out. So the mass flow rate, in other words, the mass flow rate on the inlet has to be the same as the mass flow rate on the outlet. Okay, you can always use this whenever you have situations that are in equilibrium or steady state. Okay, if you're doing a transient state, then you can't, but that's going to be a very specific case. Most cases, I'd say, call it 80% plus of the cases you'll be able to use continuity. All right, so how do we go? How does that help us? Well, if we want the exit on part C, leaving part C, and you want the exit volume flow rate, what we can do is, we know the mass flow rate already, and we happen to know a relationship that relates the mass flow rate and the volume flow rate, right? Since we're after the volume flow rate, then we can just do the reverse of what we did before, and that is the volume flow rate will just be the mass flow rate, which we know, in or out, same, times the specific volume. The specific volume, if it's the same, then the mass flow, the volumetric flow rate on the outlet is going to be exactly the same. However, the specific volume is a measure. It's dependent on the temperature and the pressure, and both of these changed. Both the temperature and the pressure changed. So we're going to have some changes here. So we need to account for those. Once we account for those, we can put the specific volume in there and then calculate what we need. Okay, so what has changed? Well, this temperature is not the same anymore. This temperature is now 50, so 10 less, so 3, 2, 3. And the pressure is significantly smaller, right? It's 0.2 now. Everything else is the same, and therefore we can leave there. But this means that this guy here is going to be greater, right? And I got this to be 479.57 times 10 to the minus 3, like the other one. All right, here we go. With this, then we can just plug that into the mass flow rate. That has to be the same, and therefore our volumetric flow rate can be calculated. So I'm going to grab this guy here, and I'm going to note that the volumetric flow rate out will be equal to the mass flow rate out times specific volume. And the other thing I can relate, if I want to, is because the specific volume and the volumetric flow rate are related, I can actually also do a ratio between the two. So either way works. So in this case here, what we have, do we want to have it per hour, or do we want to have it per second? Paste this guy here, and then for the mass flow rate, I'm going to go ahead and use this number here. This gives me that the volumetric flow rate on the outlet is 2.12929, so let's go ahead and say 1.13, and the units will be meters cubed per seconds. Cool. Now, do we have any other options for this? Yes, we do. What we can do is relate, because there's a relationship between the mass flow rates. If we go here and think about this relationship here, let me just put this one down for a second. Okay, it's the same idea, but the other thing you can think about is if there's a relationship between the mass flow rates and the mass flow rate is related to these guys here, well, we can use this in another way. I can substitute what I have mass flow rate. I can substitute the volumetric flow rate and specific volume. So I can say volume flow rate in divided by specific volume in has to be equal to volume flow rate out, specific volume out. Okay, and if that's the case, if I'm looking for, let me do this, if I'm looking for volumetric flow rate out, I can just do the volumetric flow in, which we happen to know, and that's 4.52, and then times the ratio between the specific volumes. So that will be the 479.57 times 10 to the minus 3 divided by the 28.25 times 10 to the minus 3. These guys go away, and and so there's going to be the same thing but then per hours, obviously. This is 76.73 meters cubed per hour, and if you convert that to per seconds by dividing by 3600, we get the 2.13, right? So the same answer, obviously. And that does it for part C. Part D, what do we need to do? Part D, the exit velocity of the gas. So we basically are working our way backwards, because we found everything here for the first state here on the inlet, and now we're doing kind of the reverse of it for the outlet, because we're still using exactly the same relationship for part D, right? Exactly the same, nothing new. Where is our relationship? Here it is. Okay, so if we found that if we know that the pipe is constant, so the area is always the same, and we happen to know the volumetric flow rate and the mass flow rate and the specific volume, we can choose to use this relationship here to find the velocity, or obviously this equals this to find velocity. I find the former to be easier. There's one less term for you to worry about, so let's go ahead and do that. The velocity will just be the volumetric flow rate divided by the cross-sectional area. The volumetric flow rate that we just found is 2.13 times 10 to the minus 2 divided by the cross-sectional area, which we found earlier to be 1.256 times 10 to the minus 4. Unit-wise, what we have here is meters cubed per second, and we have meters squared here. So we're going to be left with meters per second, which is great. That's what we're looking for. Velocity, and that gives me 169.698. So let's go ahead and approximate this to 170. Okay, so 170 meters per second is the out velocity. Let me put it here. V out. It might be obvious at this point, but I'm using volumetric flow rate as vol with a dot and V for velocity so that it doesn't get confused. Okay, so up until now, we've been using the same relationship over and over again. Now we get to part E, and part E is a bit more complicated. Where is part E? The rate of heat transfer to the nitrogen in the pipe. So what do we need to do here? Well, we need to do a mass balance, an energy balance. And what I'm going to do is I'm going to copy this. I'm going to copy this, and I'm going to relate this down here for part E. Okay, so let's do this. Part E. If this is my control volume, okay, let's think about the energy that's going in. We have particles coming in, and they have a certain energy related to their enthalpy because of the mass going in and the mass going out. And we also have the energy related to the kinetic energy because we have a velocity on the inlet, and we just found out the velocity on the outlet. Velocity on the outlet, right? So what we can do here is do a little energy balance in this pipe, and the pipe's going to be there in the center. Pipe's going to be in the center, and we're going to have kinetic energy in. We're going to have enthalpy in from state 1 is from the inlet, enthalpy out from the outlet, kinetic energy out. And obviously that has to be 0. So first law tells us we cannot create or destroy energy, so therefore, unless there's a heat source going in or out that we would need to relate here, there isn't. So what we need to do is say that the state of enthalpy in plus kinetic energy in has to be equal to enthalpy out plus kinetic energy out. If we were to break this down, we can break this down into, this is mass velocity squared over 2. This 2 mass velocity squared over 2. This here is an ideal gas, so we can break it down with that idea from the beginning, relating the C sub P. Where is it? Here. The C sub P, we can relate that back into enthalpy. And also remember that they gave us the K that we haven't used so far. This is where the K is going to play a role. So we can use a C sub P, specific heat, to be able to calculate the change in enthalpy.